By now, most of you will have played with these little software-defined receivers that we call dongles. The SDR-RTL has been around now for 5 to 7 years. It's gone through various generations of innovations and upgrades. And this is not another one of those dongle videos. There are literally hundreds of resources and videos out there on this. I'm not going to bore you with something like that. What I would like to do is take you through the development of an up converter that will allow you to do long wave, broadcast, or shortwave and translate it up to one of these devices. Actually, the older legacy devices can be reused with something like this. So this video is all about developing a very effective up converter system for these dongles. I hope you enjoy this series. So by now you guys have had these things in your hands for 5 years or so. You've gone through all the generations of dongles. You've probably got 2 or 3 of them in your drawer. You've learned how to use the various software programs that are out there. You've been picking up aircraft transmissions, paging, doing some simple decoding, AM, FM, some of the ham bands you've been monitoring with these, and you've pretty much gotten bored with them by now, and you put them back in the drawer. Let's pep that up again by doing a project that can use these older dongles, especially the ones that don't tune as wide a band or have as good performance as the more modern ones, and get some reuse out of them by putting a very efficient converter in front of them and up-converting the low frequencies up through the shortwave bands up to a band that some of these dongles can tune, and we're going to make a nice little shortwave receiver out of your dongle. So you guys are all familiar with the SDR Sharp. This is a Generation 4 dongle, and I'm just using a simple set of rabbit ears on it. It's going into a small netbook. It's just a simple dual atom netbook, very cheap. And this is useful for all the regular things that you can do with an SDR-RTL. So essentially what we're going to be building is a block converter. What a block converter does is it takes a band of frequencies and shifts it either up or down in frequency. In this case, we're going to take the entire HF band, and we'll start with the 2 to 30 megahertz band, and we're going to translate that up to a higher frequency that the dongle can tune. The dongle software, and there's various softwares out there, allows you to put in an offset that will make the screen look like you're tuning the low frequency shortwave bands. Now, the entire thing, even if done haphazardly with some crude printed circuit board technology, could easily fit on a board about this size. But I'm going to purposely overbuild it, or build it out on a larger piece where we can use some of our more primitive prototyping techniques, such as Manhattan style, ugly style, and so on. Because I want people to actually try to build this. The parts themselves, if done on an efficient multi-layer board, you've seen what they've been able to accomplish with some of these converters that you can buy today. Some of them are half the size of the dongle. They're so small. So we'll go through the pros and cons of the converters, the filters that are necessary, the strength of the mixer that is required to get good performance, and we'll handle the pre and the post filtering and amplification, as well as the termination on the mixer ports. I am going to start with a passive mixer, a diode mixer. So enjoy this video series on converting your dongle. The RTL-SDR is a clever implementation of a couple of chips that were designed for the Euro digital TV market, and they're made into a basic receiver that can utilize the USB port on an ordinary PC, along with some software to make a basic SDR dongle. These chips were produced in enough quantity that the pricing is low and production and available stock should continue to exist for a while longer. These dongles have been around for several years now, and the architecture is fairly standard in what we would call a reference design. Yes, there have been modest innovations and improvements in the generations of these dongles, but the basic circuits are really all the same. Two tuner devices are being utilized. The single conversion R820 chip that converts the input to an intermediate frequency that's sampled by the RTL-2832 chip. The other popular tuner chip is the E4000, which is a direct conversion I&Q device. You will notice that one artifact of direct conversion with the E4000 is the noise hump in the center of the screen. There are fans and critics of each front-end type, and I have examples of and have played with both types. I don't have any particular drama to report putting one over the other. They both work very well. We know that each bit of an A to D allows 6 dB of theoretical dynamic range. So we get 6 times 8, or 48 dB of total dynamic range with this system. And that's when everything's going right. We probably end up with more like 40 dB. My message is, you want to make darn sure that you're using all of that dynamic range in the most effective way possible. Receiving signals from DC to daylight is decidedly not the way to do this. Remember that every signal in the passband is sharing those 8 bits. Do you think that maybe the FM band, paging signals, or the cellular bands might be hogging some of your precious dynamic range? The same goes for our approach to the HF band. Simply having a low-pass filter on the front of our converter sounds great. It's very simple. We get it all, baby. But the AM broadcast band will tend to dominate, even with modest filtering, and the ability to dig out weak signals in the shortwave region or in the long wave region will be severely impacted. So as a minimum, we need to carefully plan out how we intend to deal with signals that we're not interested in, and design the up converter accordingly. Oh, and did I mention the use of tuned antennas? I don't mean to sound harsh, but it's facts of lifetime. Forget the long wire. You will enjoy tremendous signal and selectivity, freedom from broadcast band interference and so on, freedom from overload by utilizing a horizontal tuned loop or dipole. Why horizontal? Broadcast band signals are vertical in polarization, so a horizontal dipole is going to give you exceptional shortwave reception. As always, the antenna is the most important part of any radio system. Start with a simple 80 or 40 meter dipole. You'll be very surprised at the results. KA7EOI says in his blog, if the unit doesn't just overload, there will likely be issues with trying to receive weak signals in the presence of strong ones. And with just 8 bits of A to D conversion, if that difference is greater than 40 dB, you may see significant degradation. When used in the normal mode, where the R820 chip is acting as a frequency converter, the A to D converter in the RTL-2832 chip sees a somewhat limited spectrum owing to filtering in the 820 chip. That's a good thing. But despite this filtering, there is still the problem of weak versus strong signals that are within this passband, not to mention the fact that it doesn't take a lot of signal to overload the R820 outright. Of course, attenuation is one way to reduce the offending signals to the point where you're still in the linear conversion range. What happened to my weak signal once I put an attenuator right up at the antenna? It's gone. Here are a couple of approaches. Here's how we could handle this weak, strong signal problem. We could do a broadcast band stop or trap filter. This can do a lot to help. It takes out the whole broadcast band. We could design a sharp bandpass filter that starts at 2 MHz, just above the broadcast band, and stops at, say, 30 MHz. Or we could design a long wave filter. Let's say we're interested in just long wave. That would be a very sharp low-pass filter that ends up at 550 kHz, just below the broadcast band. If you happen to be a broadcast band guy, you just want to receive broadcast band, you could make a broadcast band specific filtering system with attenuation. These filtering approaches at least give the converter a chance. Most of the converters on the market attempt something like this, I sincerely hope they do. Another approach is to design a series of band-specific filters all off a dual-pole rotary switch. So these are all selectable front-end filters, selectable bandpass filters. Sounds like a lot of work, and it gets pretty large, but the results will be very impressive. Essentially, you're mimicking a Collins dual conversion scheme with a fixed front end and tunable second IF. Approach 3 is a bit crazier. Get an old-fashioned triple variable capacitor and develop some inductors for 2 or 3 bands to cover the broadcast band specifically, low shortwave, and high shortwave. So again, we're basing all of these ideas on the original mode, which is the single conversion superheterodyne, not the direct sampling mode that bypasses the tuner on the chip. So again, we're going to build a simple high-performance HF front end and up converter, and we're going to see if some of these techniques work to give us higher performance with our dongles. So you guys have to forgive me for some of these schematics that I have stolen off the internet. A lot of these guys have developed their own circuits and published them, and I'll try to give credit as I go along. This first circuit by the Russian amateur uses the SA612, the 602, that type of Gilbert cell converter is very popular for general purpose converter work, and that's a good choice. It's not going to have the dynamic range or the high signal capability that a diode type ring mixer would have, but it will give you a good noise figure and good sensitivity. So this would work very well. I've decided to go the high level route and use a ring mixer like some of these circuits here. When we get into my circuit, I probably will start simple and just try to convert a small range up, and then we will expand it as I go. But this is the circuit I'm working with. It should provide much more dynamic range than the SDR-RTL has, so it will not be the limiting factor. That said, we still have to control the gain. This is a starting point where we begin to develop circuits one at a time, and the first circuit we're going to develop is the oscillator. For our shortwave up converter, we're going to need a crystal oscillator operating between 40 and 120 megahertz. And this calls for an oscillator style called an Overtone Oscillator. Typically, the crystal will be cut for 1/3 of the frequency that you want to operate on. Sometimes there are fifth overtone crystals that are used at the higher frequencies, so the fundamental cut of the crystal is 5 times lower than the actual output frequency that you're operating on. You might recognize this transistor tester I've got here. It's really just a old-fashioned Colpitts no-tune circuit oscillator that I use to test the activity of crystals, and I use to test the gain of transistors at high frequencies. So I've got a 9 megahertz crystal in there, and I've got a transistor some of you might recognize that do a lot of RF work. It's the 2N5109. It's quite a useful transistor for QRP rigs and such, has a lot of gain, and it's an NPN, so you flick it into NPN and you can see the meter is moving. That means that the Colpitts oscillator is working at 9 megahertz. I don't want to use a power transistor like that for a simple oscillator. I'd rather use something like a 2N3904, something like that. So we'll put away these more elegant transistors, and we'll stick a 2N3904 in there. Let's see if I've got one. Yeah. Let's try this one. If I can get it in the socket. And it works. So an ordinary 2N3904 is going to work fine. It has plenty of gain. It's a good transistor. That's all I'm doing with this tester. I just want to make sure I have a good transistor that can work at a fundamental of 10 megahertz or so. And that'll work as an overtone with enough feedback. Now the overtone oscillator, let's look at that a little bit. Really, it looks just like a regular Colpitts oscillator, except you can't really see all the constants. I'm going to put a bypass capacitor here, and then this goes to whatever voltage we're going to use over here. So this is VCC out there. Now, in order for this guy to operate as a Colpitts oscillator, you have some stray capacitance here. Okay, I'm drawing that with a dotted line. And you need to set up some feedback with a capacitor here. And the X sub C that you're going for there is around 200 ohms. So at 40 megahertz, that comes out to like an 18 to a 22 puff cap. That's what we're going to use here. And biasing depends on your VCC. We can put something here like a 15K, and this one here will be adjustable until we get it into the Class A region. The tune circuit is going to be tuned for whatever our output frequency is. If it's a 40 megahertz output that we're looking for, we will tune this circuit to 40 megahertz. So that's going to be, you know, a fairly small coil. I don't know, maybe 1 microhenry, and, you know, 20 or 30 puff here on this trimmer. Any small, cheap trimmer like this would work fine in a circuit like that. Now, even though the crystal is usually operating at 1/3 of the frequency of the output, you will not find any of the fundamental frequency in the output. It's kind of like a guitar string that's operating on its harmonic. There's absolutely no energy at the fundamental coming in a 1/3 overtone oscillator. So don't worry about filtering out a product that does not exist. We will do some filtering on the output, but a well-designed oscillator will only put frequencies out on the frequency it's designed for and its harmonics. And hopefully the harmonics are well above the frequencies we're interested in. Our favorite subject is, of course, winding coils for oscillators. Everybody enjoys this. This is where you go shopping for exotic mixes of ferrites and powdered iron cores, and trying to find impossible to locate adjustable slug coils and transformers and all kinds of RF chokes and coils that become the breaking point of any project. But this is a great frequency, up around 40, 50, 60 megahertz. You really don't need much inductance at all to make a good tuned circuit. So for our test oscillator, which I'm going to build on this little piece of single-sided copper, I've decided to use a simple low-cost trimmer, so any fixed inductor will work to make the oscillator go. So we're going to wind an air-wound coil on a Bic pen. So we're going to start simply with 25 turns, close wound, on the pen. So let's put the coil on the pen, and we'll see where we end up. Okay, 25 turns, air wound on a Bic pen, and this is number 22 enamel wire. This is our starting point for our 40 megahertz, 30 megahertz, whatever, inductor for the oscillator. Okay, I can already hear some haters out there that don't like my coil, but I stuck a good old channel 14 crystal in. It's a 1/3 overtone, 27.125 megahertz as a starting point. And it is oscillating. Kind of hard to see on the screen, but not the prettiest thing in the world, but I have not set the biasing yet. I have an 18K against a 10K on the base. Let's see if she is indeed at 27 megahertz. 27.123. So it's a little bit low in frequency. So that scope was driving me crazy. The trigger was very unstable. And I finally got mad and popped the cover off the scope. And it turned out to be a contact on the time division switch. And a couple squirts of contact cleaner, and now the scope is fixed. Isn't that something? The sine wave is not terrible on the oscillator, and the biasing's not bad. I can take the voltage from, we're about 12 volts. I can take it down to just about 5 volts, and it still remains oscillating. So, got a pretty good oscillator here. I'll touch up the biasing a little bit, try to clean up that sine wave just a touch. And I think that oscillator will be okay. Next I want to put the real crystals I'm going to be using, which are 40 megahertz crystals in. And it looks like we've got too much inductance. If this thing's double tuning down at 27 megahertz, I think we can get away with a little bit less inductance. So now I have the 40 megahertz crystal in line, and look at that sine wave. Interestingly enough, the 40 megahertz crystal is happier with the constants in the circuit. The feedback, the 18 puff capacitor, and the parasitic capacitance that's in the transistor are better suited for 40 megahertz than for 27 megahertz, and the biasing remains very good down to 5 volts. It's solid as a rock. Very nice. One problem though, as I put the trimmer through its paces, I do not have double tuning. It's just on the very highest, the very lowest capacitance that I get oscillation. So the inductor is much too big. We need to take a few turns off. Too much inductance for 40. So let me show you what double tuning is. This is what we're going for with the oscillator. There should be 2 points on the trimmer in a fairly even sweep of the hemisphere of the trimmer that you get peaks. There's 1, 2. That's called double tuning. Now, we're at the very top, we're at the very low end of the trimmer's capacitance. So I've removed 5 turns, and I still have too much inductance. Also, make sure you're at 40 megahertz. So you can check that with the counter. Okay, 40 megahertz. Now, since we're at the very bottom of the capacitance range of this variable, if we go all the way meshed with this particular one, we might be able to get the crystal to oscillate on its fundamental frequency. And there it goes. Its fundamental frequency is 13 megahertz. This is a 13 megahertz crystal. Operated on its third overtone, it gives you 40 megahertz. So 13.333333 times 3 is 45 megahertz. I'm sorry, it's 40 megahertz. So I'm pretty happy with this. I'm getting double tuning now with the trimmer. So there's 1, 2, and the trimmer is not at its extremes. It's almost perfectly centered. I think this is a 35 puff trimmer, so we're probably around 15 puff, 15 turns on the big pen, and we've got a wonderful 40 megahertz oscillator that should provide good injection for just about any kind of mixer that we want to come up with. Left over from a project, who knows how old it was. I have a nice mixer here. It's a level 7 mixer. It's probably something that I picked up from leftovers from work years and years ago. It's an LMX 149. Now this is an ordinary level 7. This is an ordinary level 7 mixer. So it has 1500 megahertz on the high end, 10 megahertz on the low end. Well, how are we going to be able to use that? The way we'll use it is the IF becomes our input port. The IF port goes from 0 to 1500 megahertz. So that is going to be reassigned as the RF input. The LO will stay where it is, and the RF input will become the RF output. So that's going to become our IF, in this case, our high IF, which is the input to the SDR. So by using this mixer backwards, it should make a pretty effective converter. It will need a little bit of drive, plus 7 dBm, but I'm certain we can get that kind of power out of our one transistor oscillator. I just want to talk about coils a little bit. The oscillator was tested with both toroids and some of these air coils and the slug tune coils. And believe it or not, on a very good spectrum analyzer, the fundamental and the harmonics were almost identical. These are not the cleanest types of oscillators in the world. This is known as a power oscillator, a power Colpitts oscillator. The second harmonic was down just about 15 dB, and the third harmonic was down a little bit more than that, around 20 to 27 dB, depending on the coil. So what you have to do is you have to filter after these oscillators before sending them into the mixer. And we will be doing some filtering. Also, if you do get into the toroids, the powdered iron toroids, especially from Amidon, are excellent in this frequency range. You're starting to get to the limits of the ferrite type cores, which are more suited to broadband transformers and EMI suppression, and the lower frequencies. So you're probably going to be using those red and those yellow powdered iron cores if you decide to go with toroids. So why not a field effect transistor, an MPF 102 for instance? So what I did is I redid the circuit. Very simple field effect transistor oscillator, not much to it. And it's working very well at 12 volts, putting out a beautiful sine wave. Fewer parts. Okay, we like the FET. But let's reduce the voltage. And it starts to get squirrely. You know, the bipolar was pretty happy down around 5 volts, but the FET not so much. And if I attempt to lower the source resistor a little bit, it seems to get even squirrelier. Wants to do some VHF oscillation. So the message on the FET is it'll work fine if you give it enough voltage. I think the bipolar is a little easier to control, and it probably puts out a little more power than the FET. So in this first video we did an introduction to the SDR-RTL and how we're going to do the conversion. Went over the basic circuitry that we're going to be using. In the next video we start to solder some parts on and we start to test some components.